Welcome to Quantum Mechanics. My name is Brent Carlson. Since this is the first lecture on quantum mechanics, we have to have some sort of an introduction. And what I want to do to introduce quantum mechanics is to explain, first of all, why it's necessary, and second of all, to put it in historical context to, I'll show one of the most famous photographs in all of physics that really gives you a feel for the brain power that went into the construction of this theory. And hopefully we'll put it in some historical context as well, so you can understand where it fits in the broader philosophy of science. But the main goal of this lecture is about the need for quantum mechanics, which I really ought to just have called, Why Do We Need Quantum Mechanics? This subject has a reputation for being a little bit annoying, so why do we bother with it? Well, first off, for some historical context, imagine yourself back in 1900. Turn of the century, science has really advanced a lot. We have electricity, we have all this fabulous stuff that electricity can do, and even almost 100 years before that, physicists thought they had things figured out. There's a famous quote from Laplace, "Given for one instant an intelligence which could comprehend all the forces by which nature is animated, and the respective position of the beings which compose it, nothing would be uncertain, and the future, as the past, would be present to its eyes." Now, maybe you think intelligence which can comprehend all the forces of nature is a bit of a stretch. And maybe such a being which can know all the respective positions of everything in the universe is a bit of a stretch as well. But the feeling at the time was that if you could do that, you would know everything. If you had perfect knowledge of the present, you could predict the future. And of course you can infer what happened in the past. And everything is connected by one unbroken chain of causality. Now, in 1903, Albert Michelson, another famous quote from that time period, said, "The more important fundamental laws and facts of physical science have all been discovered. Our future discoveries must be looked for in the sixth place of decimals." Now, this sounds rather audacious. This is 1903, and he thought that the only thing that we had left to nail down was the part in a million level precision. Well, to be fair to him, he wasn't talking about never discovering new fundamental laws of physics. He was talking about really astonishing discoveries like the discovery of Uranus on the basis of orbital perturbations of Neptune. Never having seen the planet Uranus before, they figured out that it had to exist just by looking at things that they had seen. That's pretty impressive. And Michelson was really onto something. Precision measurements are really, really useful, especially today. But back in 1903, it wasn't quite so simple, and Michelson probably regretted that remark for the rest of his life. The attitude that I want you guys to take when you approach quantum mechanics, though, is not this sort of 1900s notion that everything is predicted. It comes from Shakespeare. Horatio says, "Oh, day and night, but this is wondrous strange," to which Hamlet replies, one of the most famous lines in all of Shakespeare, "And therefore as a stranger give it welcome. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." So that's the attitude I want you guys to take when you approach quantum mechanics. It is wondrous strange, and we should give it welcome. There are some things in quantum mechanics that are deeply non-intuitive, but if you approach them with an open mind, quantum mechanics is a fascinating subject, and there's a lot of really fun stuff that goes on. Now, to move on to the necessity for quantum mechanics, there were some dark clouds on the horizon, even at the early 20th century. Michelson wasn't quite having a big enough picture in his mind when he said that everything was down to the sixth place of decimals. The dark clouds on the horizon, at least according to Kelvin here, were a couple of unexplainable experiments. One, the black body spectrum. Now, a black body you can just think of as a hot object. And a hot object, like, for example, the coils on an electrical stove, when they get hot, will glow. And the question is, what color do they glow? Do they glow red? Do they glow blue? What is the distribution of radiation that is emitted by a hot object? Another difficult to explain experiment is the photoelectric effect. If you have some light and it strikes a material, electrons will be ejected from the surface. And as we'll discuss in a minute, the properties of this experiment do not fit what we think we know about, or at least what physicists thought they knew about the physics of light and the physics of electrons at the turn of the 20th century. The final difficult experiment to explain is bright line spectra. For example, if I have a flame coming from, say, a Bunsen burner, and I put a chunk of something, perhaps sodium, in that flame, it will emit a very particular set of frequencies that looks absolutely nothing like a black body. We'll talk about all of these experiments in general, or in a little bit more detail in a minute or two, but just looking at these experiments now, these are all experiments that are very difficult to explain, knowing what we knew at the turn of the 20th century about classical physics. And they're also experiments that involve light and matter. So we're really getting down to the details of what stuff is really made of and how it interacts with the things around it. These are some pretty fundamental notions, and that's where quantum mechanics really got its start. So let's pick apart these experiments in a little more detail. The black body spectrum, as I mentioned, you can think of as the light that's emitted just by a hot object. And while hot objects have some temperature associated with them, let's call that T. The plot here on the right is showing very qualitatively, I'll just call it the intensity of the light emitted as a function of the wavelength of that light. So short wavelengths, high energy, long wavelengths, low energy. Now if you look at T equals 3500 Kelvin curve here, it has a long tail to long wavelengths, and it cuts off pretty quickly as you go to short wavelengths. So it doesn't emit very much high energy light. Whereas if you have a much hotter object, 5500 Kelvin, it emits a lot more high energy light. The red curve here is much higher than the black curve. Now if you try to explain this, knowing what early 20th century physicists knew about radiation and about electrons and about atoms and how they could possibly emit light, you get a prediction. And it works wonderfully well up until about here, at which point it blows up to infinity. Infinities are bad in physics. This is the Rayleigh-Jeans law, and it works wonderfully well for long wavelengths, but does not work at all for short wavelengths. That's called the ultraviolet catastrophe, if you've heard that term. On the other end of things, if you look at what happens down here, well, it's not so much a prediction but an observation, but there's a nice formula that fits here. So on one side we have a prediction that works well on one end but doesn't work on the other. And on the other hand we have a sort of empirical formula called Wien's law that works really well at the short wavelengths, but, well, also blows up to infinity at the long wavelengths. Both of these blowing up things are a problem. And the question is, how do you get something that explains both of them? This is the essence of the black body spectrum and how it was difficult to interpret in the context of classical physics. The next experiment I mentioned is the photoelectric effect. This is sort of the opposite problem. It's not how a material emits light, it's how light interacts with the material. So you have light coming in, and the experiment is usually done like this. You have your chunk of material, typically a metal, and when light hits it, electrons are ejected from the surface, hence the electric part of the photoelectric effect. And you do all this in a vacuum, and the electrons are then allowed to go across a gap to some other material, another chunk of metal, where they strike this metal. And the experiment is usually done like this. You connect it up to a battery. So you have your material on one side and your material on the other, and you have light hitting one of these materials and ejecting electrons. And you tune the voltage on this battery such that your electrons, when they're ejected, never quite make it. So the electric field produced by this voltage is opposing the motion of the electrons. When that voltage is just high enough to stop the motion of the electrons, keep them from completely making it all the way across, we'll call that the stopping voltage. Now, it turns out that what classical E&M predicts, as I mentioned, doesn't match what actually happens in reality. But let's think about what does classical E&M predict here. Well, classical electricity and magnetism says that electromagnetic waves here have electric fields and magnetic fields associated with them, and these are propagating waves. If I increase the intensity of the electromagnetic wave, that means the magnitude of the electric field involved in the electromagnetic wave is going to increase. And if I'm an electron sitting in that electric field, the energy I acquire is going to increase. That means V stop is going to increase, because I'll have to have more voltage to stop a higher energy electron, as would be produced by a higher intensity beam of light. The other parameter of this incoming light is its frequency. So we can think about varying the frequency. If I increase the frequency, I have more intense light. Now, that doesn't say anything about the string, if I increase the frequency, I don't necessarily have more intense light. The electric field magnitude is going to be the same, which means the energy and the stopping voltage will also be the same. Now, it turns out what actually happens in reality does not match this at all. In reality, when the intensity increases, the energy, which I should really write as V stop, the stopping voltage necessary, doesn't change. And when I increase the frequency, the voltage necessary to stop those electrons increases. So this is sort of exactly the opposite. What's going on here? That's the puzzle in explaining the photoelectric effect. Just to briefly check your understanding, consider these plots of stopping voltage as a function of the parameters of the incident light, and check off which you think shows the classical prediction for the photoelectric effect. The third experiment that I mentioned is bright line spectra. And as I mentioned, this is what happens if you take a flame or some other means of heating a material, like the bar of sodium I mentioned earlier. This will emit light, and in this case, the spectrum of light from red to blue of sodium looks like this. Actually, I'm sorry, that's not sodium, that's mercury. These are four different elements: hydrogen, mercury, neon, and xenon. And instead of getting a broad, continuous distribution, like you would from a black body, under these circumstances where you're talking about gases, you get these very bright regions. It's the spectrum, instead of looking like a smooth curve like this, looks like spikes. Those bright lines are extraordinarily difficult to explain with classical physics, and this is really the straw that broke the camel's back, broke classical physics' back, that really kicked off quantum mechanics. How do you explain this? This is that famous photograph that I mentioned. This is really the group of people who first built quantum mechanics. Now, I mentioned three key experiments. The black body spectrum. This guy figured that out. This is Planck. The photoelectric effect. This guy, who I hope needs no introduction, this is Einstein, figured that out. This is the paper that won Einstein the Nobel Prize. And as far as the bright line spectra of atoms, it took a much longer time to figure out how all of that fit together. And it took a much larger group of people. But they all happen to be present in this photograph. There's this guy, and this guy, and these two guys, and this guy. This photograph is famous because these guys worked out quantum mechanics. But that's not the only, these aren't the only famous people in this photograph. You know this lady as well. This is Marie Curie. This is Lorentz, which if you studied special relativity, you know Einstein used the Lorentz transformations. Pretty much everyone in this photograph is a name that you know. I went through and looked up who these people were, these were all of the names that I recognized, which doesn't mean that the people whose names I didn't recognize weren't also excellent scientists. For example, C.T.R. Wilson here, one of my personal favorites, inventor of the cloud chamber. This is the brain trust that gave birth to quantum mechanics, and it was quite a brain trust. You had some of the most brilliant minds of the century working on some of the most difficult problems of the century. And what's astonishing is they didn't really like what they found. They discovered explanations that made astonishingly accurate predictions, but throughout the history you keep seeing them disagreeing, like, no, that can't possibly be right. Not necessarily because the predictions were wrong or they thought there was a mistake somewhere, but because they just disliked the nature of what they were doing. They were upending their view of reality. Einstein, in particular, really disliked quantum mechanics to the day that he died, just because it was so counterintuitive. And so with that introduction to a counterintuitive subject, I'd like to remind you again of that Shakespeare quote, "There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." Try to keep an open mind, and hopefully we'll have some fun at this. Knowing that quantum mechanics has something to do with explaining the interactions of light and matter, for instance, in the context of the photoelectric effect, or black-body radiation, or bright-line spectra of atoms and molecules, one might be led to the question of when is quantum mechanics actually relevant? The domain of quantum mechanics is unfortunately not a particularly simple question. When does it apply? Well, on the one hand, you have classical physics, and on the other hand, you have quantum physics. And the boundary between them is not really all that clear. On the classical side, you have things that are certain, whereas on the quantum side, you have things that are uncertain. What that means in the context of physics is that on the classical side, things are predictable. They may be chaotic and difficult to predict, but in principle they can be predicted. Well, on the quantum side, things are predictable too, but with a caveat. In the classical side, you determine everything. Basically, every property of the system can be known with perfect precision, whereas in quantum mechanics, what you predict are probabilities. And learning to work with probabilities is going to be the first step to getting comfortable with quantum mechanics. The boundary between these two realms, when the uncertain and probabilistic effects of quantum mechanics start to become relevant, is really a dividing line between things that are large and things that are small. And that's not a particularly precise way of stating things. Doing things more mathematically, quantum mechanics applies, for instance, when angular momentum L is on the scale of Planck's constant, or the reduced Planck's constant, h bar. Now, h bar is the fundamental scale of quantum mechanics, and it appears not only in the context of angular momentum. Planck's constant has units of angular momentum, so if your angular momentum is of order Planck's constant or smaller, you're in the domain of quantum mechanics. We'll learn more about uncertainty principles later as well, but uncertainties in this context have to do with products of uncertainties. For instance, the uncertainty in the momentum of a particle times the uncertainty in the position of the particle. This, if it's comparable to Planck's constant, is also going to give you the realm of quantum mechanics. Energy and time also have an uncertainty relation, again, approximately equal to Planck's constant. Most fundamentally, the classical action, when you get into more advanced studies of classical mechanics, you'll learn about a quantity called the action, which has to do with the path a system takes as it evolves in space and time. If the action of the system is of order Planck's constant, then you're in the quantum mechanical domain. Now, Planck's constant is a really small number. It's 1.05 times 10 to the negative 34 kilogram meters squared per second. times 10 to the negative 34 is a small number. So if we have really small numbers, then we're in the domain of quantum mechanics. In practice, these guys are the most useful, whereas this is the most fundamental. But we're more interested in useful things than we are in fundamental things, after all. For example, the electron in the hydrogen atom. Now, you know from looking at the bright line spectra that this should be in the domain of quantum mechanics. But how can we tell? Well, to use one of the uncertainty principles as a calculation, consider the energy. The energy of an electron in a hydrogen atom is, let's say about 10 electron volts. If we say that's p squared over 2m, using the classical kinetic energy relation between momentum and kinetic energy, that tells us that the momentum, p, is going to be about 1.7 times 10 to the minus 24th kilogram meters, kilogram, where'd it go? Where's my eraser? Kilogram meters per second. Now, this suggests that the momentum of the electron is, non-zero. But if a hydrogen atom itself is not moving, we know the average momentum of the electron is 0. So if the momentum of the electron is going to be 0 with still some momentum being given to the electron, this is more the uncertainty in the electron momentum than the electron momentum itself. The next quantity, if we're looking at the uncertainty relation between momentum and position, is we need to know the size of, or the uncertainty in the position of the electron, which has to do with the size of the atom. Now, the size of the atom, that's about 0.1 nanometers, which, if you don't remember the conversion from nanometers, is 10 to the minus 10th meters. So let's treat this as delta x, our uncertainty in position, because we don't really know where the electron is within the atom, so this is a reasonable guess at the uncertainty. Now, if we calculate these two things together, delta p, delta x, you get something, I should say this is approximate because this is very approximate, 1.7 times 10 to the negative 34th, and if you plug through the units, it's kilogram meter squared per second. This is about equal to h bar. So this tells us that quantum mechanics is definitely important here. We have to do some quantum in order to understand this system. As an example of another small object that might have quantum mechanics relevant to it, this is one that we would actually have to do a calculation. I don't know intuitively whether a speck of dust in a light breeze is in the realm of quantum mechanics or classical physics. Now, I went online and looked up some numbers. For a speck of dust, let's say the mass is about 10 to the minus 6th kilograms, a microgram. It has a velocity in this light breeze of, let's say, 1 meter per second. And make myself some more space here. The size of this speck of dust is going to be about 10 to the minus 5 meters. So these are the basic parameters of this speck of dust in a light breeze. Now we can do some calculations with this. For instance, momentum. Well, in order to understand quantum mechanics, there's some basic vocabulary that I need to go over. So let's talk about the key concepts in quantum mechanics. Thankfully, there are only a few. There's really only 3, and the first is the wave function. The wave function is, and always has been, written as psi, the Greek letter. My handwriting gets a little lazy sometimes, and it'll end up just looking like this, but technically, it's supposed to look something like that. Details aren't important, provided you recognize the symbol. Psi is a function of position, potentially in 3 dimensions, x, y, and z, and time. And the key fact here is that psi is a complex function, which means that while x, y, z, and t here are real numbers, psi, evaluated at a particular point in space, will potentially be a complex number with both a real and imaginary part. What is subtle about the wave function, and we'll talk about this in great detail later, is that while it represents the state of the system, it doesn't tell you with any certainty what the observable properties of the system are. It really only gives you probabilities. So for instance, if I have a coordinate system, something like this, where say this is position in the x direction, psi, with both real and imaginary parts, might look something like this. This could be the real part of psi, and this could be, say, the complex or the imaginary part of psi. What is physically meaningful is the squared magnitude of psi, which might look something like this in this particular case. And that is related to the probability of finding the particle at a particular point in space. As I said, we'll talk about this later, but the key facts that you need to know about the wave function is that it's complex and it describes the state of the system, but not with certainty. The next key concept in quantum mechanics is that of an operator. Now, operators are what connect psi to observable quantities. That is one thing operators can do. Just a bit of notation, usually we use hats for operators. For instance, x hat or p hat are operators that you'll encounter shortly. Operators act on psi. So if you want to apply, for instance, the x hat operator to psi, you would write x hat psi. As if this were something that as it appears on the left of psi, the assumption is that x acts on psi. If I write psi x hat, doesn't necessarily mean that x hat acts on psi. You assume operators act on whatever lies to the right. Likewise, of course, p hat psi. Now, we'll talk about this in more detail later, but x hat, the operator, can be thought of as just multiplying by x. So if I have psi as a function of x hat psi is just going to be x times psi of x. So if psi was a polynomial, you could multiply x by that polynomial. The p operator, p hat, is another example, is a little bit more complicated. This is just an example now, and technically this is the momentum operator, but we'll talk more about that later. It's equal to minus h bar times the derivative with respect to x. So this is again something that needs a function, needs the wave function to actually give you anything meaningful. Now the important thing to note about the operators is that they don't give you the observable quantities either. But in quantum mechanics, you can't really say the momentum of the wave function. For instance, p hat psi is not, and I'll put this in quotes because you won't hear this phrase very often, the momentum of psi. It's the momentum operator acting on psi, and that's not the same thing as the momentum of psi. The final key concept in quantum mechanics is the Schrödinger equation. And this is really the big equation. So I'll write it big. I, h bar, partial derivative of psi with respect to time is equal to h hat, that's an operator, acting on psi. Now h hat here is the Hamiltonian, which you can think of as the energy operator. So the property of the physical system that H is associated with is the energy of the system. And the energy of the system can be thought of as a kinetic energy. So we can write a kinetic energy operator plus a potential energy operator together acting on psi. And it turns out the kinetic energy operator can be written down. This is going to end up looking like minus h bar squared over 2m partial derivative of psi with respect to, second partial derivative of psi with respect to position, plus, and then the potential energy operator is going to look like the potential energy as a function of position just multiplied by psi. So this is the Schrodinger equation. Typically, you'll be working with it in this form. So I h bar times the partial derivative with respect to time is related to the partial derivative with respect to space, and then multiplied by some function. The basic quantum mechanics that we're going to learn in this course mostly revolves around solving this function and interpreting the results. So to put these in a bit of a roadmap, we have operators. We have the Schrodinger equation. And we have the wave function. Now operators act on the wave function, and operators are used in the Schrodinger equation. Now the wave function that actually describes the state of the system is going to be the solution to the Schrodinger equation. Now I mentioned operators acting on the wave function. What they give you when they act on the wave function is some property of the system, some observable perhaps. And the other key fact that I mentioned so far is that the wave function doesn't describe the system perfectly, it only gives you probabilities. So that's our overall concept map. To put this in the context of the course outline, the probabilities are really the key feature of quantum mechanics, and we're going to start this course with a discussion of probabilities. We'll talk about the wave function after that and how the wave function is related to those probabilities, and we'll end up talking about operators and how those operators and the wave functions together give you probabilities associated with observable quantities. That will lead us into a discussion of the Schrodinger equation, which will be most of the course, really. The bulk of the material before the first exam will be concerned with various examples. Solution to the Schrodinger equation under various circumstances. This is really the main meat of quantum mechanics in the beginning. After that, we'll do some formalism. And what that means is we'll learn about some advanced mathematical tools that make keeping track of all the details of how all of this fits together a lot more straightforward. And then we'll finish up the course by doing some applications. So those are our key concepts and a general roadmap through the course. Hopefully now you have the basic vocabulary necessary to understand phrases like the momentum operator acts on the wave function, or the solution to the Schrodinger equation describes the state of the system, and that sort of thing. Don't worry too much if these concepts haven't quite clicked. In order to really understand quantum mechanics, you have to get experience with them. These are not things that you really have any intuition for based on anything you've seen in physics so far. So bear with me, and this will all make sense in the end, I promise. Complex numbers, or numbers involving, conceptually you can think about it as the square root of -1, I, are essential to understanding quantum mechanics, since some of the most fundamental concepts in quantum mechanics, for instance the wave function, are expressed in terms of complex numbers. Complex analysis is also one of the most beautiful subjects in all of mathematics, but unfortunately, in this course I don't have the time to go into the details. Lucky you, perhaps. Here's what I think you absolutely need to know to understand quantum mechanics from the perspective of complex analysis. First of all, there's the basic definition. I squared is equal to -1, which you can think of also as I equals the square root of -1. In general, a complex number, z, then, can be written as the sum of a purely real part, x, and a purely imaginary part, I times y. Note in this expression, z is complex, x and y are real, where I times y is purely imaginary. The terms purely real or purely imaginary in the context of this expression like this, x plus iy, something is purely real if y is 0, something is purely imaginary if x is 0. As far as some notation for extracting the real and imaginary parts, typically mathematicians will use this funny calligraphic font to indicate the real part of x plus iy or the imaginary part of x plus iy, and that just pulls out x and y. Note that both of these are real numbers. When you pull out the imaginary part, you get x and y. You don't get iy, for instance. Another one of the most beautiful results in mathematics is e to the I pi plus 1 equals 0. This formula kind of astonished me when I first encountered it, but it is a logical extension of this more general formula that e raised to a purely imaginary power, iy, is equal to the cosine of y plus I times the sine of y. This can be shown in a variety of ways, in particular involving the Taylor series. If you know the Taylor series for the exponential, the Taylor series for cosine of y, and the Taylor series for sine of y, you can show quite readily that the Taylor series for complex exponential is the Taylor series of cosine plus the Taylor series of sine. And while that might not necessarily constitute a rigorous proof, it's really quite fun if you get the chance to go through it. At any rate, the trigonometric functions here, cosine and sine, should be suggestive, and there is a geometric interpretation of complex numbers that we'll come back to in a minute. But for now, know that while we have rectangular forms like this, x plus iy, where x and y, the nomenclature there is chosen on purpose, you can also express this in terms of r e to the I theta, where you have now a radius and an angle. The angle here, by the way, is going to be the arctangent of y over x. And we'll see why that is in a moment when we talk about the geometric interpretation. But given these rectangular and polar forms of complex numbers, what do the basic operations look like? How do we manipulate these things? Well, addition and subtraction in rectangular form is straightforward. If we have two complex numbers, a plus ib plus, and we want to add to that a second complex number, c plus id, we just add the real parts, a and c, and we add the imaginary parts, b and d. This is just like adding in any other sort of algebraic expression. Multiplication is a little bit more complicated. You have to distribute, and you distribute in the usual sort of draw a smiley face kind of way. A times c and b times d are going to end up together in the real part. And the reason for that is, well, a times c, a and c both being real numbers, a times c will be real. Whereas ib times id, both being purely complex numbers, you'll end up with b times d times I squared, and I squared is minus 1. So you just end up with minus bd, which is what we see here. Otherwise, the complex part is perhaps a little more easy to understand. You have I times b times c, and you have a times I times d, both of which end up with plus signs in the complex part. Division, in this case, is like rationalizing the denominator, except instead of involving radicals, you have complex numbers. If I have some number a plus ib divided by c plus id, I can simplify this by both multiplying and dividing by c minus id. Note the sign change in the denominator here. C plus id is then prompting me to multiply by c minus id over c minus id. Now, when you do the distribution there, for instance, let's just do it in the denominator, c plus id times c minus id, my top eyebrows here of the smiley face, c squared times id, or c squared plus, now, id times minus id, which is, well, I'll just write it out, I times minus id, which is going to be d squared times I times minus I. So I squared times minus 1, and I squared is minus 1. So I have minus 1 times minus 1, which is just 1, so I can ignore that. I just got d squared. So what I end up with in the denominator is just c squared plus d squared. What I end up with in the numerator, well, that's the same sort of multiplication thing that we just discussed. So the simplified form of this has no complex part in the denominator, which helps keep things a little simple and a little easier to interpret. Now in polar form, addition and subtraction, well, they're complicated. Under most circumstances, if you have two complex numbers given in polar form, it's easiest just to convert to rectangular form and add them together there. Multiplication and division, though, in polar form have very nice expressions. Q e to the I theta times R e to the I phi. Well, these are just all real numbers multiplying together, and then I can use the rules regarding multiplication of exponentials, meaning if I have two things like e to the I theta and e to the I phi, I can just add the exponents together. It's like taking x squared times x to the fourth and getting x to the sixth. But QR e to the I theta plus phi. So that was easy. We didn't have to do any distribution at all. The key fact here is that you add the angles together. In the case of division, it's also quite easy. You simply divide the radii, q over r, and instead of adding, you subtract the angles. So polar complex numbers expressed in polar form are much easier to manipulate in multiplication and division, while complex numbers represented in rectangular form are much easier to manipulate for addition and subtraction. Taking the magnitude of a complex number, usually we'll write that as something like z, if z is a complex number, just using the same notation for absolute value of a real number, usually is expressed in terms of the complex conjugate. Now, the complex conjugate, notationally speaking, is usually written by whatever complex number you have, here in this case x plus iy, with a star after it. And what that signifies is you flip the sign on the complex part, on the imaginary part. X plus iy becomes x minus iy. The squared magnitude then, which is always going to be a real and positive number, this absolute value squared notation, is what you get from multiplying a number by its complex conjugate. And that's what we saw earlier with c plus id. Say I take the complex conjugate of c plus id and multiply it by c plus id. Well, the complex conjugate of c plus id is c minus id times c plus id. And doing the distribution, like we did when we calculated the denominator, when we were simplifying the division of complex numbers in rectangular form, just gave us c squared plus d squared. This should be suggestive if you have something like x plus iy, that's really messy, x plus iy, and I want to know the squared absolute magnitude. Thinking about this as a position in Cartesian space should make this formula, c squared plus d squared in this case, just make a little more sense. You can also, of course, write that in terms of real and imaginary parts. But let's do an example. If w is 3 plus 4i, and z is minus 1 plus 2i, first of all, let's find w plus z. Well, w plus z is 3 plus 4i plus minus 1 plus 2i. That's straightforward. If you can keep track of your terms, 3 minus 1 is going to be our real part, so that's 2. And 4i plus 2i, which is plus 6i, is going to be our complex part. Sorry, our imaginary part. Now, w times z. 3 plus 4i times minus 1 plus 2i. For this, we have to distribute, like usual. So from our top eyebrow terms here, we've got 3 times minus 1, which is minus 3, and 4i times 2i, both positive. So I have 4 times 2, which is 8, and I times I, which is minus 1, minus 8. Then, for my imaginary part, I guess the mouth and the chin, if you want to think about it that way, I have 4i times minus 1, minus 4 with the I out front, will just be minus 4 inside the parentheses here, and 3 times 2i is going to give me 6i, plus 6 inside. The end result you get here is 8, or minus 8 minus 3 is minus 11, and minus 4 plus 6 is going to be 2. So I get minus 11 plus 2i for my multiplication here. I guess if I'm going to circle that answer, I should circle this answer as well. Now, slightly more complicatedly, w over z. W is 3 plus 4i, and z is minus 1 plus 2i. And you know when you want to simplify an expression like this, you multiply by the complex conjugate of the denominator divided by the complex conjugate of the denominator. So minus 1 minus 2i divided by minus 1 minus 2i. And if we continue the same sort of distribution, I'll do the numerator first. Same sort of multiplication we just did here, only the signs will be flipped a little bit. We'll end up with minus 3 plus 8 instead of minus 3 minus 8. And for the imaginary part, we'll end up with minus 4 minus 6 instead of minus 4 plus 6. And you can work out the details of that distribution on your own if you want. The denominator is not terribly complicated, since we know we're taking the absolute magnitude of a complex number by multiplying a complex number by its complex conjugate. We can just write this out as the square of the real part, 1, plus the square of the imaginary part, minus 2, which squared is 4. So if I continue this final step, this is going to be 5. This is going to be minus 10i, and our denominator here is just going to be 5. So in the end, what I'll end up with is going to be 1 minus 2i. So it actually ended up being pretty simple in this case. Now for the absolute magnitude of w, 3 plus 4i, you can think of this as w times w star square root. You can think of this as the square root of the real part of w plus the imaginary part of w. Sorry, square root of the squared of the real part plus the square of the imaginary part, which is perhaps a little easier to work with in this case, so you don't have to distribute out complex numbers in that way. Real part is 3, imaginary part is 4. So we end up with the square root of 3 squared plus 4 squared, which is 5. Now this was all in rectangular form. Let me move this stuff out of the way a little bit. And let's do it again, at least a subset of it, in polar form. In polar form, w, 3 plus 4i, we know the magnitude of w, that's 5. So that's going to be our radius, 5. And our e to the I theta, where theta is, like I said, the arctan. Since complex numbers are so important to quantum mechanics, let's do a few more examples. In this case, I'm going to demonstrate how to manipulate complex numbers in a more general way, not so much just doing examples with numbers. First example, simplify this expression. You have two complex numbers multiplied in the numerator, and then a division. First of all, the first thing to simplify is this multiplication. You have x plus iy times ic. This is pretty easy. It's a simple sort of distribution. We're going to have x times ic. That's going to be a complex part. So I'm going to write that down a little bit to the right, ixc. And then we're going to have iy times ic, which is going to be minus yc. That's going to be real. We also have a real part in the numerator from d here, so I'm going to write this as d minus yc plus ic. That's the result of multiplying this out. That's then going to be divided by f plus ig. Now, in order to simplify this, you have a complex number in the denominator. You know you need to multiply by the complex conjugate and divide by the complex conjugate. So f minus ig divided by f minus ig. Now, expanding this out is a little bit messier, but fundamentally you've seen this sort of thing before. You have real part, and imaginary part in the numerator. And then you're going to have imaginary part, and real part, imaginary part. And what you're going to end up with from this first term, you get f times d minus yc. From the second term, you have minus ig times ixc, which is going to give you xcg. We have a minus I times an I, which is going to give us a plus. Incidentally, if you're having trouble figuring out something like minus I times I, think about it in the geometric interpretation. This is I in the complex plane. This is minus I in the complex plane. So I have one angle going up, one angle going down. If I'm multiplying them together, I'm adding the angles together. So I essentially go up and back down, and I just end up with 1 equals I times minus I. Otherwise, you can keep track of I squareds equals minus 1s and just count up your minus signs. This, then, is the real part. Suppose I should write that in green, lest my fonts gets too confusing. Excuse me. So that's the real part. The imaginary part, then, is what you get from these terms here. I'm going to write an I out front, and now we have xc times f, so xcf with an I from here, and then we have d minus yc times ig, which I'll just write as g d minus yc. In the denominator, we're now multiplying a number by its complex conjugate. You know what to do there. F squared plus g squared. This is just the magnitude of this complex number. Sorry, squared magnitude. Now, this doesn't necessarily look more simple than what we started with, but this is effectively fully simplified. You could further distribute this and distribute this, but it's not really going to help you very much. The thing to notice about this is that the denominator is purely real. We've also separated out the real part of the numerator and the imaginary part of the numerator. Yeesh. My handwriting is getting messier as I go. Imaginary part of the numerator. So we can look at this numerator now and say, this is the complex number, real part, imaginary part, and then it's just divided by this real number, which effectively is just a scaling. It's a relatively simple thing to do, to divide by a real number. As a second example, consider solving this equation for x. Now this is the same expression that we had in the last problem, only now we're solving it for it equal to 0. So from the last page, I'm going to borrow that first simplification step we did, distributing this through. We had d minus yc for the real part, plus ixc for the imaginary part, and that was divided by f plus ig. If we're setting this equal to 0, the nice part about dealing with complex expressions like this is that 0, treated as a complex number, is 0 plus 0i. It has a real part and an imaginary part as well. It's just kind of trivial. And in order for this complex number to be equal to 0, the real part must be 0 and the imaginary part must be 0. So we can think of this as d minus yc plus ixc. This has to equal 0 and this has to equal 0 separately. So we effectively have two equations here, not just one, which is nice. We have d minus yc equals 0 and xc equals 0, which, unless c equals 0, just means x equals 0. That's the only way that this equation can hold, is if x equals 0. The key fact here is to keep in mind that in order for two complex numbers to be equal, both the real parts and the imaginary parts have to be equal. As a slightly more involved example, consider finding the cubed roots of 1. Now, you know 1 cubed is 1. That's a good place to start. We'll see that fall out of the algebra pretty quickly. What we're trying to do is solve the equation z cubed equals 1, which you can think of as x plus I y, where x and y are real numbers, cubed, equals 1. Now, if we expand out this cubic, you get x cubed plus 3x squared times iy plus 3x times iy squared plus iy cubed. and this is going to have to equal 1. Excuse me, equal 1. Now, looking at these expressions, here we have an iy, here we have an iy squared. This is going to give me an I squared, which is going to be a minus sign. And here I have an iy cubed. This is going to give me an I cubed, which is going to be minus I. So I have two complex parts and two real parts. So I'm going to rewrite that. X cubed, and then now a minus sign from the I squared, 3xy squared, plus, pulling an I out front, the imaginary part then is going to come from this 3x squared y and this y cubed. So I've got a 3x squared y here, and then a minus y cubed, minus coming from the I squared. And this is also going to have to equal 1. Now, in order for this complex number to equal this complex number, both the real parts and the imaginary parts have to be equal. So let's write those two separate equations. X cubed minus 3xy squared equals the real part of, this is the real part of the left-hand side, has to equal the real part of the right-hand side, 1. And the imaginary part of the left-hand side, 3x squared y minus y cubed, has to equal the imaginary part of the right-hand side, 0. So those are our two equations. This one in particular is pretty easy to work with. We can simplify this. This is, we can factor a y out. This is y times 3x squared minus y squared equals 0. One possible solution then is going to come from this. You have a product like this is equal to 0. Either this is equal to 0 or this is equal to 0. And saying y equals to 0 is rather straightforward. So let's say y equals 0, and let's substitute that into this expression. That's going to give us x cubed equals 1, which might look a lot like the equation we started with, z cubed equals 1, but it's subtly different because z is a general complex number, whereas our assumption in starting the problem this way is that x is a purely real number. So a purely real number, which when cubed gives you 1, that means x equals 1. So x equals 1, y equals 0, that's one of our solutions. Z equals 1 plus 0i, or just z equals 1. Now, we could have told me that right off the bat, z cubed equals 1. Well, one possible solution is that z equals 1, since 1 cubed is 1. The other thing we can do here is we can say 3x squared minus y squared is equal to 0. This means that, I'll just cheat a little bit and simplify this, 3x squared equals y squared. Now I can substitute this y squared, into this expression as well. And what you end up with is x cubed minus 3x, and then y squared was equal to 3x squared. So 3x squared is going to go in there. That has to equal 1. Now let's move up here. What does that leave us with? That says x cubed minus 9x cubed equals 1. So minus 8x cubed equals 1. This means x, again, being a purely real number, is equal to minus 1/2. Minus 1/2 times minus 1/2 times minus 1/2 times 8 times minus 1 is equal to 1. You can check that pretty easily. Now, where does that leave us? Where did I go? That leaves us substituting this back into this expression, which tells us that 3x squared equals y squared. X equals minus 1/2, so 3 minus 1/2 squared equals y squared, which tells you that y equals plus or minus the square root of 3/4 if you finish your solution. So now we have two solutions for y here coming from one value for x, and that gives us our other two solutions to this cubic, we have a cubic equation. We would expect there to be 3 solutions, especially when we're working with complex numbers like this. And this is our other solution. Z equals minus 1/2 plus or minus the square root of 3/4 I. So those are our 3 solutions. Now, finding the cubed roots of 1 to be these complex numbers is not necessarily particularly instructive. However, there's a nice geometric interpretation. The cubed roots of unity like this, the nth roots of unity, doesn't have to be a cubed root. All lie on a circle of radius 1 in the complex plane. And if you check the complex magnitude of this number and the complex magnitude of this number, you will find that it is indeed unity. To check your understanding of this, a slightly simpler problem is to find the square roots of I. Put another way, you've got Z, some generic complex number here, equals to x squared plus x plus iy. Quantity squared, if that's going to equal y, we'll expand this out, solve for x and y in the 2 equations that will result from setting real and imaginary parts equal to each other. And same as with the cubed roots of 1, the square roots of I will also fall on a circle of radius 1 in the complex plane. So those are a few examples of how complex numbers can actually be manipulated. In particular, finding the roots of unity, there are better formulas for that than the approach that we took here, but I feel this was hopefully instructive.
If probability is at the heart of quantum mechanics, what does that actually mean? Well, the fundamental source of probability in quantum mechanics is the wave function psi. Psi tells you everything that you can in principle know about the state of the system, but it doesn't tell you everything with perfect precision. How that actually gives rise to probability distributions in observable quantities like position or energy or momentum is something that we'll talk more about later, but from the most basic perspective, psi can be thought of as related to a probability distribution. But let's take a step back and talk about probabilistic measurements in general first. If I have some space, let's say it's position space. Say this is the floor of a lab, and I have a ball that is somewhere on the floor. I can measure the position of that ball. Maybe I measure the ball to be there on the floor. If I prepare the experiment in exactly the same way, attempting to put the ball in the same position on the floor and measure the position of the ball again, I won't always get the same answer because of perhaps some imprecision in my measurements or some imprecision in how I'm reproducing the system. So I might make a second measurement there, or a third measurement there. If I repeat this experiment many times, I'll get a variety of measurements at a variety of locations. And maybe they cluster in certain regions, or maybe they're very unlikely in other regions. But this distribution of measurements, we can describe that mathematically with a probability distribution. A probability distribution, for instance, I could plot P of x here, and P of x tells you roughly how many, or how likely you are to make a measurement. So I would expect P of x as a function to be larger here, where there's a lot of measurements, and 0 here where there's no measurements, and relatively small here where there's few measurements. So P of x might look something like this. The height of P of x here tells us how likely we are to make a measurement in a given location. This concept of a probability distribution is intimately related to the wave function. So the most simple way that you can think of probability in quantum mechanics is to think of the wave function psi of x. Now psi of x, you know, is a complex function, and a complex number can never really be observable. What would it mean, for example, to measure a position of, say, 2 plus 3i meters? This isn't something that's going to occur in the physical universe. But the fundamental interpretation of quantum mechanics that this book in particular, that most physicists think of, is the interpretation that psi, in the context of a probability distribution, the absolute magnitude of psi squared is related to the probability of finding the particle described by psi. So if the squared magnitude of psi is large at a particular location, that means it is likely that the particle will be found at that location. Now the squared magnitude here means that we have to take the squared magnitude of psi. We can't just take psi itself. So for instance, in the context of the plot that I just made on the last page, if this is x and our y-axis here is psi, psi has real and imaginary parts. So the real part of psi might look something like this, and the imaginary part might look something like this. And the squared magnitude would look something like, well, what you can imagine the squared magnitude of that function looking like. You can think of the squared magnitude of psi as the probability distribution. Let me move this up a little bit, give myself some more space. The squared magnitude of psi then can be thought of as a probability distribution in the likelihood of finding the particle at a particular location, like I said. Now, what does that mean mathematically? Mathematically, suppose you had two positions, A and B, and you wanted to know what the probability of finding the particle between A and B was. Given a probability distribution, you can find that by integrating the probability distribution. So the probability that the particle is between A and B is given by the integral from A to B of the squared absolute magnitude of psi dx. You can think of this as a definition. You can think of this as an interpretation. But fundamentally, this is what the physical meaning of the wave function is. It is related to the probability distribution of position associated with this particular state of the system. Now, what does that actually mean? And that's a bit of a complicated question. It's very difficult to answer. Suppose I have a wave function, which I'm just going to write as the plot as the squared magnitude of psi now. Suppose it looks something like this. Now that means I'm perhaps likely to measure the position of the particle somewhere in the middle here. So suppose, wrong color. So suppose I do that. Suppose I measure the position of the particle here. So I've made a measurement now. Messy handwriting. I've made a measurement, and I've observed the particle to be here. What does that mean in the context of the wave function? Now, everything that I can possibly know about the particle has to be encapsulated in the wave function, so after the measurement, when I know the particle is here, you can think of the wave function as looking something like this. It's not going to be infinitely narrow because there might be some uncertainty. The width of this is related to the precision of the measurement. But the wave function before the measurement was broad, like this, and the wave function after the measurement is narrow. What actually happened here? What about the measurement caused this to happen? This is one of the deep issues in quantum mechanics that is quite difficult to interpret. So what do we make of this? Well, one thing that you could think, just intuitively, is that, well, this probability distribution wasn't really all the information that was there. Really, the particle was there. Let's say this is point C. One interpretation is that the particle really was at C all along. That means that this distribution reflects ignorance on our part as physicists, not fundamental uncertainty in the physical system. This turns out to not be true, and you can show mathematically and in experiments that this is not the case. The main interpretation that physicists use is to say that this wave function psi here, also shown here, collapses. Now that's a strange term, collapses. But it's hard to think of it any other way. Suppose you were concerned with the wave function's value here. Before the measurement, it's non-zero, whereas after the measurement, it's 0. So this decrease in the wave function out here is, it's reasonable to call that a collapse. What that wave function collapse means is subject to some debate, and there are other interpretations. One interpretation that I'll mention very briefly, but we won't really discuss very much, is the many worlds interpretation, and that's that when you make a measurement like this, the universe splits. So it's not that the wave function all of a sudden decreases here, it's that for us, in our tiny little chunk of the universe, the wave function is now this, and there's another universe somewhere else where the wave function is this, because the particle was observed to be here. Don't worry too much about that, but the interpretation issues in quantum mechanics are really fascinating once you start to get into them. You can think about this as the universe splitting into, splits. The universe, you can think about this as the universe splitting into many little sub-universes where the probability of where the particle is observed at a variety of locations. One location per universe, really. This question of how measurements take place is really fundamental, but hopefully this explains a little bit of where probability comes from in quantum mechanics. The wave function itself can be thought of as a probability distribution for position measurements. And unfortunately, the measurement process is not something that's particularly easy to understand, but that's the fundamental origin of probability in quantum mechanics. To check your understanding, here is a simple question about probability distributions and how to interpret them. Variance and standard deviation are properties of a probability distribution that are related to the uncertainty. Since uncertainty is such an important concept in quantum mechanics, we need to know how to quantify how uncertainty results from probability distributions. So let's talk about the variance and the standard deviation. These questions are related to the shape of a probability distribution. So if I have a set of coordinates, let's say this is the x-axis, and I'm going to be plotting then the probability density function as a function of x. Probability distributions come in lots of shapes and sizes. You can have probability distributions that look like this, probability distributions that look like this. You can even have probability distributions that look like this, or probability distributions that look like this. And these are all different. The narrow peak here versus the broad distribution here. The distribution with multiple peaks, or multiple modes, in this case it has two modes, so we call this distribution bimodal, or multimodal. And then this distribution, which is asymmetric, has a long tail in the positive direction and a short tail in the negative direction. We would say this distribution is skewed. So distributions have lots of different shapes, and if what we're interested in is the uncertainty, you can think about that roughly as the width of the distribution. For instance, if I'm drawing random numbers from the orange distribution, the narrow one here, they'll come over roughly this range. Whereas if I'm drawing from the blue distribution, they'll come over roughly this range. So if this were, say, the probability density for position, say this is the squared magnitude of the wave function for a particle, I know where the particle represented by the orange distribution is much more accurately than the particle represented by the blue distribution. So this concept of width of a distribution and the uncertainty in the position, for instance, are closely related. The broadness is related to the uncertainty. This is fundamental to quantum mechanics, so how do we quantify it? In statistics, the broadness of a distribution is called the variance. variance is a way of measuring the broadness of a distribution, for example. So suppose this is my distribution. The mean of my distribution is going to fall roughly in the middle here. Let's say that's the expected value of x if this is the x-axis. Now, if I draw a random number from this distribution, I won't always get the expected value. Suppose I get a value here. If I'm interested in the typical deviation of this value from the mean, that will tell me something about how broad this distribution is. So let's define this displacement here to be delta x. Delta x is going to be equal to x minus the expected value of x. And first of all, you might think, well, if I'm looking for the typical values of delta x, let's just try the expected value of delta x. Well, what is that? Unfortunately, the expected value of x doesn't really work for this purpose because delta x is positive if you're on this side of the mean and negative if you're on this side of the mean. So the expected value of delta x is 0. Sometimes it's positive, sometimes it's negative, and they end up canceling out. Now, if you're interested in only positive numbers, the next guess you might come up with is let's use not delta x, but let's use the absolute value of delta x. What is that? Well, absolute values are difficult to work with since you have to keep track of whether a number is positive or negative and keep flipping signs if it's negative. So this turns out to just be kind of painful. What statisticians and physicists do in the end then is instead of taking the absolute value of a number to make it positive, we square it. So you calculate the expected value of the squared deviation, sort of the mean squared deviation. This has a name in statistics. It's written as sigma squared, and it's called the variance. To do an example, let's do a discrete example. Suppose I have two probability distributions, all with equally likely outcomes. Say the outcomes of one distribution are 1, 2, and 3, while the outcomes for the second distribution are 0, 2, and 4. Put it graphically, these numbers are more closely spaced than these numbers. So I would expect the broadness of this distribution to be larger than the broadness of this distribution. You can calculate this out by calculating the mean squared deviation. So first of all, we need to know the mean. The expected value of x is 2 in this case, and also in this case. Knowing the expected value of x, you can calculate the deviations. So let's say delta x here is going to be minus 1, 0, and 1 are the possible deviations from the mean for this probability distribution, whereas in this case it's minus 2, 0, and 2. Then we can calculate the delta x squareds that are possible, and you get 1, 0, and 1 for this distribution, and 4, 0, and 4 for this distribution. Now when you calculate the mean of these squared deviations, in this case, the expected value of the squared deviation is 2/3, whereas in this case, the expected value of the squared deviation is 8/3. So indeed, we did get a larger number for the variance in this distribution. So you can think of that as the definition. This is not the easiest way of calculating the variance, though. It's actually much easier to calculate the variance as an expected value of a squared quantity and minus the square of the expected value of the quantity itself. So the mean of the square minus the square of the mean, if that helps you to remember it. You can see how this results fairly easily by plugging through some basic algebra. So given our definition, the expected value of delta x squared, we're calculating an expected value. So suppose we have a continuous distribution now. The continuous distribution expected value has an integral in it, so we're going to have the integral of delta x squared times rho of x dx. Now delta x squared, we know what delta x is. Delta x is x minus the expected value of x, so we can plug that in here.
and we're going to get the integral of x minus expected value of x squared times rho of x dx. I can expand this out, and I'll get integral of x squared minus 2x expected value of x plus expected value of x quantity squared rho of x dx. And now I'm going to split this integral up into three separate pieces. First piece, integral of x squared rho of x dx. Second piece, integral of 2x expected value of x rho of x dx. And the third piece, integral of expected value of x squared rho of x dx. Now this integral you recognize right away. This is the expected value of x squared. This integral, I can pull this out front since this is a constant. This is just a number. This is the expected value. So this integral is going to become 2. I can pull the 2 out, of course, as well. 2 times the expected value of x, and then what's left is the integral of x, rho of x, dx, which is just the expected value of x. This integral, again, this is a constant, so I can pull it out front. And when I do that, I end up with just the integral of rho of x dx. And we know the integral of rho of x dx over the entire domain. I should specify that this is the integral from minus infinity to infinity now. All of these are integrals from minus infinity to infinity. The integral of minus infinity to infinity of rho of x dx is 1. So this, after I pull the expected value of x quantity squared out, is just going to be the expected value of x quantity squared. So this is expected value of x squared. This is, well, I can simplify this as well. This is the expected value of x quantity squared as well. So I'm going to erase that and say squared there. So I have this minus twice this plus this. And in the end, that gives you expected value of x squared minus the expected value of x squared. So, mean of the square minus the square of the mean. To check your understanding of how to use this formula, I'd like you to complete the following table. Now, I'll give you a head start on this. If your probability distribution is given by 1, 2, 4, 5, and 8, all equally likely, you can calculate the mean. Now once you know the mean, you can calculate the deviations, x minus the mean, which I'd like you to fill in here. Then square that quantity and fill it in here, and take the mean of that squared deviation. Same as what we did when we talked about the variance as the mean squared deviation. Then, taking the other approach, I'd like you to calculate the squares of all of the x's and calculate the mean square. You know the mean square. You can calculate this quantity, mean of the square minus the square of the mean, and you should get something that equals the mean squared deviation. That's about it for variance, but just to say a little bit more about this, variance is not the end of the story. It turns out there's more. I mentioned the distributions that we were talking about earlier on the first slide here. Keep forgetting to turn my ruler off. The distributions that look like this versus distributions that look like this. This is a question of symmetry, and the mathematical name for this is skew, or skewness. There's also distributions that look like this versus distributions that look like this. And this is mathematically, this is called kurtosis, which kind of sounds like a disease or perhaps a villain from a comic book. Kurtosis has to do with the relative weights of things near the peak versus things in the tails. Now, mathematically speaking, you know the variance, let me go back a little further. You know the mean, that was related to the integral of x, rho of x, dx. We also just learned about the variance, which was related to the integral of x squared, rho of x, dx. It turns out the skewness is related to the integral of x cubed, rho of x, dx, and the kurtosis is related to the integral of x to the fourth, rho of x, dx. At least those are common ways of measuring skewness and kurtosis. These are not exact formulas for skewness and kurtosis, nor is this an exact formula for the variance, of course, so I'm taking some liberties with the math. But you can imagine, well, what happens if you take the integral of x to the fifth, rho of x dx? You could keep going, and you would keep getting properties of the probability distribution that are relevant to its shape. Now, you won't hear very much about skewness and kurtosis in physics, but I thought you should know that this field does sort of continue on. For the purposes of quantum mechanics, what you need to know is that variance is related to the uncertainty, and we will be doing lots of calculations of variance on the basis of probability distributions derived from wave functions in this class. We talked a little bit about the probabilistic interpretation of the wave function psi. That's one of the really remarkable aspects of quantum mechanics, that there are probabilities rolled up in your description of the physical state. We also talked a fair amount about probability itself, and one of the things we learned was that probabilities had to be normalized, meaning the total sum of all of the probable outcomes, the probabilities of all of the outcomes in a probability distribution has to equal 1. That has some implications for the wave function, especially in the context of the Schrödinger equation, so let's talk about that in a little more detail. Normalization in the context of a probability distribution just means that the integral from minus infinity to infinity of rho of x dx is equal to 1. You can think about that as the sort of extreme case of the probability that, say, x is between a and b being given by the integral from a to b of rho of x dx. In the context of the wave function, that statement becomes the probability that the particle is between a and b is given by the integral from a to b of the squared magnitude of psi of x integrated between a and b. So this is the same sort of statement. You're integrating from a to b, and in the case of the probability density, you have just the probability density. In the case of the wave function, you have the squared absolute magnitude of the wave function. This is our probabilistic interpretation. We're sort of making an analogy between psi, squared magnitude, and a probability density. This normalization condition, then, has to also hold for psi, if the squared magnitude of psi is going to be treated as a probability density. So, integral from minus infinity to infinity of squared absolute magnitude of psi dx has to equal 1. This is necessary for our statistical interpretation of the wave function. This brings up an interesting question, though, because not just any function can be a probability distribution. Therefore, this normalization condition, treating psi as a probability density, means there are some conditions on what sorts of functions are allowed to be wave functions. This is the question of normalizability. Suppose, for instance, I had a couple of functions that I was interested in. Say one of those functions looks sort of like this, keeps on rising as it goes to infinity. If I wanted to consider the squared magnitude of this function, this is our possible psi. This is our possible psi squared. Sorry about the messy there. This function, since it's going to, it's continuing to increase as x increases, both in the negative direction and in the positive direction, its squared magnitude is going to look something like this. I can do a little better there, sorry. If I tried to, say, calculate the integral from minus infinity to infinity of this function, I've got a lot of area out here from, say, 3 to infinity, where the wave function is positive. This would go to infinity, therefore. What that means is that this function is not normalizable. Not all functions can be normalized. If I drew a different function, for example, something that looked maybe something like this, its squared magnitude might look something like this. There is a finite amount of area here, so if I integrated the squared magnitude of the blue curve, I would get something finite. What that means is that whatever this function is, I could multiply or divide it by a constant such that this area was equal to 1. I could take this function and convert it into something such that the integral from minus infinity to infinity of the squared magnitude of psi equaled 1, and it obeyed our sort of statistical constraint on the probability distribution. In order for this to be possible, psi has to have this property, and the mathematical way of stating it is that psi must be square integrable. And all this means is that the integral from minus infinity to infinity of the squared magnitude of psi is finite. You don't get 0, you don't get infinity. In order for this square integrability to hold, for example, though, you need a slightly weaker condition that psi goes to 0 as x goes to either plus or minus infinity. It's not possible to have a function that stays non-zero or goes to infinity itself as x goes to infinity and still have things be integrable. Like I said, if this holds, if this integral here is finite, you can convert any function into something that is normalized by just multiplying or dividing by a constant. Is that possible, though? In the Schrodinger equation, does multiplying or dividing by a constant do anything? Well, the Schrodinger equation here you can just glance at it and see that multiplying and dividing by a constant doesn't do anything. The Schrodinger equation is I h bar partial derivative with respect to time of psi equals minus h bar squared over 2m second derivative of psi with respect to position plus the potential times psi. Now, if I made the substitution psi went to some multiple or some constant a multiplied by psi, you can see what would happen. Here I would have psi times a, here I would have psi times a, and here I would have psi times a. So I would have an a here, an a here, and an a here. So I could divide through this entire equation by a, and all of those a's would disappear, and I would just get the original Schrodinger equation back. What that means is that if psi solves the Schrodinger equation, a psi does too. I'll just say a psi works. Now this is only if a is a constant. Does not depend on time, does not depend on space. If a depended on time, I would not be able to divide it out of this partial derivative because the partial derivative would act on that a. Same goes for if a was a function of space. If a was a function of space, I wouldn't be able to divide it out of this partial derivative with respect to x. So this only holds if a is a constant. That means that I might run into some problems with time evolution. I can choose a constant and I can multiply psi by that constant such that psi is properly normalized at, say, time t equals 0, but will that hold for future times? It's a question of normalization in time evolution. What we're really interested in here is the integral from minus infinity to infinity of psi of x and time squared dx. If this is going to always be equal to 1, supposing it's equal to 1 at some initial time, what we really want to know is what the time derivative of this is. If the time derivative of this is equal to 0, then we'll know that whatever the normalization of this is, it will hold throughout the evolution of the wave function. Now I'm going to make a little bit of simplifying notation here, and I'm going to drop the integral limits since it takes a while to write. And we're going to manipulate this expression a little bit. We're going to use the Schrodinger equation. We're going to use the rules of complex numbers. We're going to use the rules of differential calculus. And we're going to get something that will show that indeed this does hold. So let's step through that. Manipulations of the Schrodinger equation like this are a little tricky to follow, so I'm going to go slowly, and if it seems like I'm being extra pedantic, please bear with me. Some of the details are important. So the first thing that we're going to do, pretty much the only thing that we can do with this equation, is we're going to exchange the order of integration and differentiation. Instead of differentiating with respect to time the integral with respect to x, we're going to integrate with respect to x of the time derivative of this psi of x and t quantity squared. Basically, I've just pushed the derivative inside the integral. Now, notationally speaking, I'm going to move some stuff around here, give myself a little more room. Notationally, oops, didn't mean to change the colors. Notationally speaking here, the d dt became a partial derivative with respect to time. The total derivative, d by dt, is now a partial. What the notation is keeping track of here is just the fact that this is a function only of time, since you've integrated over x and you've substituted in limits. Whereas this is a function of both space and time. So whereas this derivative is acting on something that's only a function of time, I can write it as a simple d by dt, the total derivative. In this case, since what the derivative is acting on is a function of both position and time, I have to treat this as a partial derivative now. So the next thing that we're going to do, aside from after pushing this derivative inside and converting it to a partial derivative, is rewrite this squared absolute magnitude of psi as psi star times psi. Now the squared absolute magnitude of a complex number is equal to the complex number times its complex conjugate. It's just simple complex analysis rules there. So what we've got is the integral of the partial derivative with respect to time of psi star times psi, integral dx. Now we have a time derivative applied to a product. We can apply the product rule from differential calculus. And what we end up with is the integral of the partial derivative with respect to time of psi star times psi plus psi star partial derivative of psi with respect to time. That's integrated dx. Now what I'm going to do is I'm going to notice these partial derivatives with respect to time. And I'm going to ask you to bear with me for a minute while I make a little more space. It's probably a bad sign if I'm running out of space on a computer where I have effectively infinite space. But bear with me. The partial derivatives with respect to time appear in the Schrodinger equation. I h bar d by dt of psi equals minus h bar squared over 2m partial derivative, second partial derivative of psi with respect to position plus potential times psi. These are the time derivatives that I'm interested in. I can use the Schrodinger equation to substitute in, say, the right-hand side for these time derivatives, both for psi star and for psi. So first I'm going to manipulate this by dividing through by I h bar, which gives me the partial psi partial time equals I h bar over 2m, second partial of psi with respect to x, minus, where did it go? I v over h bar psi. So that can be substituted in here. I also need to know something for the complex conjugate of psi, so I'm going to take the complex conjugate of this entire equation. What that looks like is partial derivative of psi star with respect to time. Now I'm taking the complex conjugate of this, so I have a complex part here. The sign of that needs to be flipped. And I have a complex number here that needs to be complex conjugated, since the complex conjugate of a product is the product of the complex conjugates. What that means is this is going to become minus I h bar over 2m d squared psi star dx squared. Sorry, I forgot the squared there. Plus I v over h bar psi. So I've just gone through and changed the signs on all of the imaginary parts of all these numbers. Psi became psi star, I became minus I became I. And this can be substituted in for that. And what you get when you make that substitution, this equation isn't really getting simpler, is it? It's getting longer. What you get is the integral of something. I'll put an open square brackets at the beginning here. I've got this equation, minus I h bar over 2m, second partial derivative of psi star partial x squared, plus I v over h bar psi star, that's multiplied by psi from here. So I've just substituted in this expression for this. Now the next part I have plus psi star and whatever I'm going to substitute in from this, which is what I get from this version of the Schrodinger equation here. I h bar over 2m second partial derivative of psi with respect to x minus I v over h bar psi. Close parentheses, close square brackets, and I'm integrating dx. Now, this doesn't look particularly simple, but if you notice what we've got here, this term, if I distributed this psi in, would have I v over h bar psi star times psi. This term, if I distributed this psi star in, would have an I v over h bar psi star and psi. This term has a plus sign, this term has a minus sign. So these terms actually cancel out. What we're left with, then, to rewrite things, both of the terms that remain have this minus I h bar over 2m out front. So we're going to have equals to I h bar over 2m. And here I have a minus second partial derivative of psi star with respect to x times psi. And here I have plus psi star times the corresponding second partial of psi with respect to x. And this is integrated dx. Is that all right? Yes. Now, what I'd like you to notice here is that we've got d by dx and we've got an integral dx. We don't have any time anymore. So we're making progress. And we're actually almost done. Where did we get so far? We started with the time derivative of this effective total probability, which should have been equal to 1, which would be equal to 1 if this were a proper probability distribution, but we're just considered with the time evolution, since we know that whatever psi is, we can multiply it by some constant to make it properly normalized at a particular time. Now we're interested in the time evolution. We're looking at the time derivative of this, and we've gone to this expression, which has complex conjugates of psi and second partial derivatives with respect to x. Now, what I'd like you to do, and this is a check your understanding question, is think about why this statement is true. This is the partial derivative with respect to x of psi star d psi dx minus d psi star dx. So, sorry, I'm saying d, I should be saying partial. These are partial derivatives. This is true, and it's up to you to figure out why. But since this is true, what we're left with is we have our I h bar over 2m, an integral over minus infinity to infinity of this expression, partial with respect to x of psi star partial psi partial x minus partial psi star partial x psi. We're integrating dx now. And this is nice because we're integrating dx of a derivative of something with respect to x. So that's easy. Fundamental theorem of calculus. We end up with I h bar over 2m psi star partial psi partial x minus partial psi star partial x psi, evaluated at the limits of our integral, which are minus infinity to infinity. Now, if psi is going to be normalizable, we know something about the value of psi at negative and positive infinity. If psi is normalizable, psi has to go to 0 as x goes to negative and positive infinity. What that means is that when I plug in the infinity here, psi star, d psi dx, and psi, everything here is going to be 0. So when I enter in my limits, I'm just going to get 0 and 0. So the bottom line here, after all of this manipulation, is that this is equal to 0. What that means is that the integral from negative infinity to infinity of the squared absolute magnitude of psi as a function of both x and time is equal to a constant. Put another way, time evolution does not affect normalization. What that means is that I can take my candidate wave function, not normalized, integrate it, find out what I would have to multiply or divide it by to make it normalized, and if I'm successful, I have my normalized wave function. I don't need to worry about how the system evolves in time. The Schrödinger equation does not affect the normalization. So this is that check your understanding question I mentioned. The following statement was that crucial step in the derivation, and I want you to show that this is true, explain why in your own words. Now, to do an example here, normalize this wave function. What that means is that we're going to have to find a constant, and I've already put the constant in the wave function, a, such that the integral from minus infinity to infinity of the squared absolute magnitude of psi of x, in this case I've left the time dependence out, is equal to 1. And same as in the last problem, the first thing we're going to do is substitute the squared absolute magnitude of psi for psi star times psi. The other thing I'm going to do before I get started is notice that my wave function is 0 if the absolute value of x is greater than 1, meaning for x above 1 or below negative 1. So instead of integrating from minus infinity to infinity here, I'm just going to focus on the part where psi is non-zero and integrate from minus 1 to 1. Integral from minus 1 to 1 of psi star, which is going to be a, e to the ix is going to become e to the minus ix, and 1 minus x squared is still going to be 1 minus x squared. Now, I haven't complex conjugated a because part of the assumption about normalization constants like this is usually that you can choose them to be purely real. So I'm not going to worry about taking the complex conjugate of a just to make my life a little easier. Psi, well, that's just right here, a e to the ix 1 minus x squared. I'm integrating dx. This is psi star, this is psi, integral dx from minus 1 to 1 should be equal to 1. So let's do this. We end up with a squared times the integral from minus 1 to 1 of e to the minus ix and e to the ix. What's e to the minus ix times e to the ix? Well, thinking about this in terms of the geometric interpretation, we have e to the ix, which is cosine theta plus I sine theta. You can think about that as being somewhere on the unit circle at an angle theta. Minus I theta would just be in the exact opposite direction. So when I multiply them together, I'm going to get something that has the product of the magnitudes. The magnitudes are both 1, and it's purely real. You can see that also by looking at just the rules for multiplying exponentials like this. E to the minus ix times e to the plus ix is e to the minus ix plus ix, or e to the 0, which is 1. So I can cancel these out. And what I'm left with is 1 minus x squared, quantity squared, dx. Plugging through the algebra a little further, a squared, integral minus 1 to 1, of 1 minus 2x squared plus x to the 4th dx. You can do this integral equals a squared to, x minus 2/3 x cubed plus x to the 5th over 5. We know in quantum mechanics that all of the information about the physical system is encapsulated in the wave function psi. Psi then ought to be related to physical quantities for example, position, velocity, and momentum of the particle. We know a little bit about the position. We know how to calculate things like the expected value of the position. And we know how to calculate the probability that the particle is within a particular range of positions. But what about other dynamical variables like velocity or momentum? The connection with velocity and momentum brings us to the point where we really have to talk about operators. Operators are one of our fundamental concepts in quantum mechanics, and they connect the wave function with physical quantities. But let's take a step back first and think about what it means for a quantum system to move. The position of the particle, we know, say, the integral from a to b of the squared magnitude of the wave function dx gives us the probability that the particle is between a and b. And we know that the expected position is given by a similar expression, the integral from minus infinity to infinity of psi star of x times the psi of x dx. Now these expressions are related, by the fact that the squared magnitude of psi is the probability density function describing position, and this is really just the calculation of the expected value of x given that probability density function. Now what if I want to know what the motion of the particle is? One way to consider this is, suppose I have a box, and if I know the particle is, say, here at time t equals 0, what can quantum mechanics tell me about where the particle is later? Physically speaking, you could wait until, say, t equals 1 second, and then measure the position of the particle. And maybe it would be here. You could then wait a little longer and measure the particle again. Maybe at that point it would be here. That's, say, t equals 2 seconds. Or if I wait a little bit longer and measure the particle yet again at, say, t equals 3 seconds, maybe the particle would be up here. Now, does that mean that the particle followed a path that looked something like this? No. We know that the position of the particle is not something that we can observe at any given time with impunity because of the way the observation process affects the wave function. Back when we talked about measurement, we talked about having a wave function that looked something like this, a probability density that looked something like that. And then after we measure the position of the particle, the probability density has changed. If we say measure the particle to be here, the new wave function has to accommodate that new probability density function. The fact that measurement affects the system like this means that we really can't imagine repeatedly measuring the position of a particle in the same system. What we really need is an ensemble. That's the technical term for what we need. What an ensemble means in this context is that you have many identically prepared systems. Now, if I had many identically prepared systems, I could measure the position over and over and over and over again, once per system. If I have, 100 systems, I could measure the position 100 times, and that would give me a pretty good feel for what the probability density for position measurements is at the particular time when I'm making those measurements. If I wanted to know about the motion of the particle, I could do that again, except instead of taking my 100 measurements all at the same time, I would take them at slightly different times. So instead of this being the same system, these would all be different systems that have been allowed to evolve for different amounts of time. And as such, the motion of the particle isn't going to end up looking something like that. It's going to end up looking like some sort of probabilistic motion of the wave function in space. What we're really interested in here, oh, sorry, I should make a note of that. Single measurement per system. This notion of averaging over many identically prepared systems is important in quantum mechanics because of this effect that measurement has on the system. So what we're interested in now, in the context of something like motion, is, well, can we predict this? Can we predict where the particle is likely to be as a function of time? And yes, we can. And what I'd like to do to talk about that is to consider a quantum mechanical calculation that we can actually do, the time derivative of the expected value of position. This time derivative tells us how the center of the probability distribution, if you want to think about it that way, how the center of the wave function moves with time. So this time derivative, d by dt of the expected value of x, that's d by dt of, let's just write out the expected value of x, integral from minus infinity to infinity of x times psi star of x, psi of x, where this is the probability density function that given by the wave function, and this is x. We're integrating dx. Now, if you remember when we talked about normalization and whether the normalization of the wave function changed as the wave function evolved in time, we're going to do the same sort of calculation with this. We're going to do some calculus with this expression. We're going to apply the Schrodinger equation. But as before, the first thing we're going to do is move this derivative inside the equation. This is a total time derivative of something that's a function of, in principle, position and time. I should write these as functions of x and t. And what you get when you push that in is, as before, the integral, or the total derivative becomes a partial derivative. Since x is just the coordinate x in these contexts of functions of both space and time, the total time derivative will not affect the coordinate x, even when it becomes a partial derivative. So what we'll end up with is x times the partial time derivative of psi star psi integral dx. I'm not going to write the integral from minus infinity to infinity here just to save myself some time. Now, if you remember this expression, the integral, or sorry, not the full integral, just the partial time derivative of psi star psi, that was what we worked with in the lecture on normalization. So if we apply the result from the lecture on normalization, and it's equation 126, yes, in the book,
if we apply that, you can simplify this down a lot right off the bat. And what you end up with is I h bar over 2m times this integral x, and then what we substitute in. The equation 126 gives an expression for this highlighted part here in orange. And what you get is the partial derivative with respect to x of psi star partial of psi with respect to x minus partial of psi star with respect to x times psi. Integral still with respect to dx, of course. Now, if we look at this equation, we're making the same sort of progress we made when we did the normalization derivation. We had time derivatives here. Now we have only space derivatives. And we have only space derivatives in an integral over space. So this is definitely progress. Now we can start thinking about what we can do with integration by parts. The first integration by parts I'm going to do has the non-differential part just being x, and the differential part being dv is equal to, I'm not going to have space to write this here. I'm going to move stuff around a little bit. So the differential part is dv is the partial derivative, well, what's left of this equation, the partial derivative with respect to x of psi star d psi dx minus d psi dx psi, d psi star dx psi. And then there's the dx from the integral. Sorry, I'm running out of space. This differential part here is just this part of the equation. Now I can take this derivative, du dx, in my integration by parts procedure, du equals dx, and dv here is easy to integrate because this is a derivative. So when I integrate the derivative there, I'll just end up with v equals psi star d psi dx minus d psi star dx psi. Now when I actually apply those, that integration by parts, the boundary term here without the integral in it is going to involve these two. So I'm going to have x times psi star partial psi partial x minus partial psi star partial x psi. And that's going to be evaluated between minus infinity and infinity, the limits on my integral. The integral part, which comes in with the minus sign, is going to be composed of these bottom two terms. Integral of psi star partial psi partial x minus partial psi star partial x psi, and its integral dx from minus infinity to infinity. Now what's nice, I forgot something here. What did I forget? My leading constants. I still have this IH bar over 2m out there. IH bar over 2m is multiplied by this entire expression. Now, the boundary terms here vanish. The boundary terms in integration by parts in quantum mechanics will often vanish because if you're evaluating something at, say, infinity, psi has to go to 0 at infinity, so this term is going to vanish. Psi star has to go to 0 at infinity, so this is going to vanish. So even though x is going to infinity, psi is going to 0. And if you dig into the mathematics of quantum mechanics, you can show convincingly that the limit as x times psi goes to infinity is going to be 0. So this boundary term vanishes, both at infinity and at minus infinity. And all we're left with is this. Yes. All you're left with is that. So I'll write that over. IH bar over 2m times the integral of psi star partial psi partial x minus partial psi star partial x psi integral dx. I'm actually going to split that up into two separate integrals. So I'll stick another integral sign in here, and I'll put a dx there. And I'll put parentheses around everything, so my leading constant gets multiplied in properly. And now I'm going to apply integration by parts again, but this time just to the second integral here. So here, we're going to say u is equal to psi, and dv is equal to, again, using the fact that when we do this integral, if we can integrate a derivative, that potentially simplifies things. So this is going to be partial psi star partial x dx. So when we take the derivative of this, we're going to get du is equal to partial psi partial x. And when we integrate this, we're going to get v equals psi star. Now, when we do the integration, when we write down the answer from this integration by parts, the boundary term here, psi star times psi, is going to vanish, again, because we're evaluating it at a region where both psi star and psi, vanish. So the boundary term vanishes. And you notice I have a minus sign here. When we do the integration by parts, the integral term has a minus sign in it here. So we're going to have the partial psi with respect to x and psi star, with a minus sign coming from the integration by parts and a minus sign coming from the leading term here. So we're going to end up with a plus sign there. So we get a minus from the integral part. What that means, though, is that I have psi star and partial psi partial x. In my integration by parts, I end up with partial psi partial x and psi star. It's the same. And the fact that I had a minus and another minus means I get a plus. So I have two identical terms here. The result of this, then, is I h bar over m. I'm adding a half and a half and getting 1, basically, times the integral of psi star partial psi partial x dx. And this is going to be something that I'm going to call now the expectation of the velocity vector, the velocity operator. This is the sort of thing that you get out of operators in quantum mechanics. You end up with expressions like this. And this I'm sort of equating just by analogy with the expectation of a velocity operator. This is not really a probability distribution anymore, at least not obviously. We started with the probability distribution due to psi, the absolute magnitude of psi squared, and we end up with the partial derivative on one of the psi's. So it's not obvious that this is a probability distribution anymore, and well, it's the probability distribution in velocity, and it's giving you the expected velocity in some sense, in a quantum mechanical sense. So this is really a more general sort of thing. We have the velocity operator, the expectation of the velocity operator. Oh, and operator-wise, I will try to put hats on things. I will probably forget. I don't have that much attention to detail when I'm making lectures like this. The hat notation means operator. If you see something that you really sure is an operator but it doesn't have a hat, that's probably just because I made a mistake. But this expression for the expectation of the velocity operator is the one we just derived, minus I h bar over m times the integral of psi star partial derivative of psi with respect to x integral dx. Now, it's customary to talk about momentum instead of velocity. Momentum has more meaning because it's a conserved quantity under most physics. So we can talk about the momentum operator, the expectation of the momentum operator. And I'm going to write this momentum operator expression in a slightly more suggestive way. The integral of psi star times something in parentheses here, which is minus I h bar, partial derivative with respect to x. And I'm going to close the parentheses there, put a psi after it, and a dx for the integral. You have the same sort of expression for the position operator. We were just writing that as the expected value of position without the hat earlier. But that's going to be the integral of psi star. What goes in the parentheses now is just x psi dx. So this you recognize as the expectation of the variable x, subject to the probability distribution given by psi star times psi. This is slightly more subtle. You have psi star and psi, which looks like a probability distribution, but what you have in the parentheses now is very obviously an operator that does something. It does more than just multiply by x. It multiplies by minus I h bar and takes the derivative of psi. Operators in general do that. We can write them as, say, x hat equals x times where there's very obviously something that has to go after the x in order for it to be considered an operator. Or we can say the same for v hat. It's minus I h bar over m times the partial derivative with respect to x, where there obviously has to be something that goes here. Likewise for momentum, minus I h bar partial derivative with respect to x. Something has to go there. Another example of an operator is the kinetic energy operator. Usually that's written as T, and that's minus h bar squared over 2m. You can think of it as the momentum operator squared. It's got a second derivative with respect to x. And again, there very obviously has to be something that goes there. The operator acts on the wave function. That's what I said back when I talked about the fundamental concepts of quantum mechanics, and this is what it means for the operator to act on the wave function. The operator itself is not meaningful. It's only meaningful in the context when it's acting on a wave function. In general, wrong color. In general, the expectation value of some
As an introduction to the uncertainty principle, we're going to talk about waves and how waves are related to each other. We'll get into a little bit of the context of Fourier analysis, which is something we'll come back to later. But the overall context of this lecture is the uncertainty principle. And the uncertainty principle is one of the key results from quantum mechanics, and it's related to what we discussed earlier in the context of the boundary between classical physics and quantum physics. Quantum mechanics has these inherent uncertainties that are built into the equations, built into the state, built into the nature of reality that we really can't surmount. And the uncertainty principle is one way in which those, or is the mathematical description. It's those relationships that I gave you earlier. Delta P, delta X is greater than about equal to h bar over 2. I think I just said greater than about equal to h bar earlier. We'll do things a little more mathematically here, and it turns out there's a factor of 2 there. To start off, though, conceptually think about position and wavelength. And this really is now in the context of a wave. So say I had a coordinate system here, something like this. And if I had some wave with a very specific wavelength, you can just think about it as a sinusoid. If I asked you to measure the wavelength of this wave, you could take a ruler and you could plop it down there and say, okay, well, how many inches are there from peak to peak? Or from zero crossing to zero crossing? Or if you really wanted to, you could get a tape measure and measure many wavelengths, 1, 2, 3, 4 wavelengths in this case. That would allow you to very accurately determine what the wavelength was. If, on the other hand, the wave looked more like this, give you another coordinate system here, the wave looks something like this, you wouldn't be able to measure the wavelength very accurately. You could, as usual, put your ruler down on top of the wave, for instance, and count up the number of inches or centimeters from one side to the other, but that's just one wavelength. It's not nearly as accurate as, say, measuring 4 wavelengths, or 10 wavelengths, or 100 wavelengths. You can think of some limiting cases. Suppose you had a wave with many oscillations. It looks like I'm crossing out the wave underneath there, so I'm going to erase this in a moment. But if you had a wave with many wavelengths, and you could measure the total length of many wavelengths, you would have a very precise measurement of the wavelength of the wave. The opposite is the case here. You only have one wavelength. You can't really measure the wavelength very accurately. What you can do, however, is measure the position very accurately. Here, I can say pretty certainly the wave is there, plus or minus a very short spread in position. The other hand, here, I cannot measure the position of this wave accurately at all. If this thing continues, I can't really say where the wave is. It's not really a sensical question to ask, where is this wave? This wave is everywhere. These are the sorts of built-in uncertainties that you get out of quantum mechanics. Where is the wave? The wave is everywhere. It's a wave. It doesn't have a local position. It turns out, if you get into the mathematics of Fourier analysis, that there is a relationship between the spread of wavelengths and the spread of positions. If you have a series of waves of all different wavelengths and they're added up, the spread in the wavelength will is related to the spread in positions of the sum. And we'll talk more about Fourier analysis later, but for now, just realize that this product is always going to be greater than or equal to about 1. Wavelength is something with units of inverse length, and the position, of course, is something with units of length. So the dimensions of this equation are sort of a guideline. Wavelength and position have this sort of relationship, and this comes from Fourier analysis. So how do these waves come into quantum mechanics? Well, waves in quantum mechanics really first got their start with Louis de Broglie. I always thought his name was pronounced de Broglie, but it's, well, he's French, so there's all sorts of weird pronunciations in French. De Broglie is my best guess at how it would probably be pronounced. De Broglie proposed that matter could travel in waves as well. And he did this with an interesting argument on the basis of 3 fundamental equations that had just recently been discovered when he was doing his analysis. This was in his PhD thesis, by the way. E equals mc squared. You all know that equation. You all hopefully also know this equation, E equals hf. Planck's constant times the frequency of a beam of light is the energy associated with a quanta of light. This was another one of Einstein's contributions, and it has to do with his explanation of the photoelectric effect. The final equation that de Broglie was working with was C equals f lambda. The speed of light is equal to the frequency of the light times the wavelength of the light. And this is really not true just for light. This is true for any wave phenomenon. The speed, the frequency, and the wavelength are related. Now, if these expressions are both equal to waves, or are both equal to energy, then I ought to be able to say mc squared equals hf. And this expression tells me something about f. It tells me that f equals c over lambda. So I can substitute this expression in here and get mc squared equals hc over lambda. Now I can cancel out one of the c's, and I'm left with mc equals h over lambda. Now what de Broglie said was this is like momentum. So I'm going to write this equation as p equals h over lambda. And then I'm going to wave my hands extraordinarily vigorously and say, while this equation is only true for light, and this equation is only true for waves, this is also true for matter. How actually this happened in the context of quantum mechanics, in the early historical development of quantum mechanics, is de Broglie noticed that the spectrum of the hydrogen atom, these bright line spectra that we were talking about, where a hydrogen atom emits light of only very specific wavelengths. Intensity as a function of wavelength looks something like this. But that could be explained if he assumed that the electrons were traveling around the nucleus of the hydrogen atom as waves, and that only an integer number of waves would fit. The one that I just drew here didn't end up back where it started, so that wouldn't work. If you had a wavelength that looked something like this, going around, say, 3 full times in a circle, that would potentially account for these allowed emission energies. That was quite a deep insight, and it was one of the things that really kicked off quantum mechanics at the beginning. The bottom line here, for our purposes, is that we're talking about waves, and we're talking about matter waves. So that uncertainty relation, or the relationship between the spreads of wavelengths and the spreads in positions that I mentioned in the context of Fourier analysis, will also potentially hold for matter. And that gets us into the position-momentum uncertainty relation. The wave-momentum relationship we just derived on the last slide was P equals h over lambda. This tells you that the momentum and the wavelength are related. From 2 slides ago, when we were talking about waves and whether or not you could say exactly where a wave was, we had a relationship that was something like delta lambda, the spread in wavelengths, times the spread in positions of the wave, is always greater than about equal to 1. Combining these relationships together in quantum mechanics, and this is not something that I'm doing rigorously now, I'm just waving my hands, gives you delta P, delta X is always greater than about equal to h bar over 2. And this is the correct mathematical expression of the Heisenberg uncertainty principle that we'll talk more about and derive more formally in Chapter 3. But for now, just realize that the position of a wave, the position of a particle, are uncertain quantities, and the uncertainties are related by this, which in one perspective results from consideration of adding many waves together in the context of Fourier analysis, which is something we'll talk about later as well, extended through the use of, or the interpretation of matter as also a wave phenomenon. To check your understanding, here are 4 possible wave packets, and I would like you to rank them in 2 different ways. 1, according to the uncertainties in their positions, and 2, according to the uncertainties in their momenta. So if you consider, say, wave B to have a very certain position, you would rank that one highest in terms of the certainty of its position. Perhaps you think wave B has a very low uncertainty in position, you would put it on the other end of the scale. I'm looking for something like the uncertainty of B is greater than the uncertainty of A is greater than the uncertainty of D is greater than the uncertainty of C for both position and momentum. The last comment I want to make in this lecture is on energy-time uncertainty. This was the other equation I gave you when I was talking about the boundary between classical physics and quantum physics. We had delta P delta X is greater than or equal to h bar over 2, and now we also had, excuse me for a moment here, delta E delta T greater than about equal to h bar over 2. Same sort of uncertainty relation, except now we're talking about spreads in energy and spreads in time. I'd like to make an analogy between these 2 equations. Delta P and delta X. Delta P, according to De Broglie, is related to the wavelength, which is sort of a spatial frequency. It's the frequency of the wave in space. Delta X, of course, is just, well, I'll just say that's a space. And these are related, according to this equation. In the context of energy and time, we have the same sort of thing. Delta T, well, that's pretty clear, that's time. And delta E, well, that then, therefore, by analogy here, has to have something to do with the frequency of the wave now in time. And that's simple, that's just the frequency. The fact that these are also related by an uncertainty principle tells you that there's something about energy and frequency in time. And this is something that we'll talk about in more detail in the next lecture when we start digging into the Schrödinger equation. The time-dependent Schrödinger equation and deriving the time-independent Schrödinger equation, which will give us the relationship exactly. But for now, position and momentum, energy and time, are both talking about sort of wave phenomenon, except in the context of position and momentum, you're talking about wave length, frequency of the wave in space, whereas energy and time, you're talking about the frequency of the wave in time, how quickly it oscillates. That's about all. The uncertainty principle, as I've said, is something that we'll treat in much more detail in Chapter 3. But for now, the uncertainty principle is important because you have these equations, and these are fundamental properties of the universe, if you want to think of them that way. And there's something that we're going to be working with as a way of checking the validity of quantum mechanics throughout the rest of throughout Chapter 2. That's all for now. You just need to conceptually understand how these wave lengths and positions or frequencies and times are interrelated. The last few lectures have been all about the wave function, psi. And since psi is such an important concept in quantum mechanics, Really, the first entire chapter of the textbook is devoted to the wave function and all of its various properties. Since we've reached the end of Chapter 1 now is a good opportunity to go and review the key concepts of quantum mechanics, in particular the wave function and how it is related to the rest of quantum mechanics. The key concepts, as I stated them earlier, were operators, the Schrödinger equation, and the wave function. Operators are used in the Schrödinger equation and act on the wave function. Your friend and mine, psi. What we haven't really talked about a lot yet is how to determine the wave function, and the wave function is determined as solutions to the Schrödinger equation. That's what Chapter 2 is all about, solving the Schrödinger equation for various circumstances. The key concepts that we've talked about so far, operators and the wave function, conspire together to give you observable quantities. Things like position or momentum, or say the kinetic energy of a particle. But they don't give us these properties with certainty. In particular, the wave function really only gives us probabilities. And these probabilities don't give us really any certainty about what will happen. Uncertainty is one of the key concepts that we have to work with in quantum mechanics. So let's take each of these concepts in turn and talk about them in a little more detail, since now we have some actual results that we can use, some mathematics. We can put more meat on this concept map than just simply the concept map. First, the wave function. The wave function, psi, does not tell us anything with certainty. And it's a good thing, too, because psi, as a function of position and time, is complex. It's not a real number. And it's hard to imagine what it would mean to actually observe a real number. So the wave function is already on somewhat suspect ground here. But it has a meaningful connection to probability distributions if we more or less define the squared modulus, the absolute magnitude of the wave function, to be equal to a probability distribution. And this is the probability distribution for what? Well, it's the probability distribution for outcomes of measurements of position, for instance. You can think about this as a probability distribution for where you're likely to find the particle should you go looking for it. This interpretation as a probability distribution requires the wave function to be normalized. Namely, that if I integrate the squared magnitude of the wave function over the entire space that I'm interested in, I have to get 1. This means that if I look hard enough for the particle everywhere, I have to find it somewhere. The probability distributions, as I mentioned earlier, don't tell you anything with certainty. In particular, there is a good deal of uncertainty, which we express as a standard deviation or a variance. For instance, if I'm interested in the standard deviation of the uncertainty, or standard deviation of the position, it's most easy to express as the variance, which is the square of the standard deviation. And the square of this standard deviation, or the variance, is equal to the expectation value of the square of the position minus the square of the expectation value of the position. And we'll talk about expectation values in a moment. Expectation values are calculated using expressions with operators that look a lot like these sorts of integrals. In fact, I can re-express this as the expectation of the square in terms of a probability distribution is just the x squared times multiplied by the probability distribution with respect to x, integrated over all space. This is the expectation of x squared. I can add to that, or subtract from that, the square of the expectation of x, which has a very similar form. And that gives us our variance. So our wave function, which is complex, gives us probability distributions, which can be used to calculate expectation values and uncertainties. This probabilistic interpretation of quantum mechanics gets us into some trouble pretty quickly. I'm going to move this up now, give myself some more space. Namely with the concept of wave function collapse. Now, collapse bothers a lot of people, and it should. This is really a philosophical problem with quantum mechanics, that we don't really have a good interpretation of what quantum mechanics really means for the nature of reality. But the collapse of the wave function is more or less a necessary consequence of the interpretation of the wave function as a probability distribution. If I have some space, some coordinate system, and I plot on this coordinate system the squared magnitude of psi. This is related to our probability distribution with respect to position. If I then measure the position of the particle, what I'm going to get is, say I measure the particle to be here. Now, if I measure the position of the particle again immediately, I should get a number that's not too different than the number that I just got. And this is just sort of to make sure that if I repeat a measurement, it's consistent with itself, that I don't have particles jumping around truly randomly. If I know the position, I know the position. That's a reasonable assumption. What that means is that the new probability distribution for the position of the particle after the measurement is very sharply peaked about the position of the measurement. If this transition from a wave function, for instance, that has support here to a wave function that has no support here did not happen instantaneously, it's imaginable that if I tried to measure the particle's position twice in very rapid succession, that I would have one particle measured here and another particle measured here. Does that really mean I have one particle, or do I have two particles? These particles could be separated by quite a large distance in space, and my measurements could be not separated by very much in time, so I might be getting into problems with special relativity and the speed of light. And these sorts of considerations are what leads to the Copenhagen interpretation of quantum mechanics, which centers on this idea of wave functions as probability distributions and wave function collapse as part of the measurement process. Now, I mentioned operators in the context of expectation values. Operators are our second major concept in quantum mechanics. What about operators in the wave function? Well, operators, let's just write a general operator as Q hat. Hats usually signify operators. Operators always act on something. You can never really have an operator in isolation. And what the operators act on is usually the wave function. We have a couple of operators that we've encountered, namely the position operator, x hat, which is defined as x times. And what's it multiplied by? Well, it's multiplied by the wave function. We also have the momentum operator, p hat, and that's equal to minus I h bar times the partial derivative with respect to x of what? Well, of the wave function. We also have the kinetic energy, which I'll write as ke hat. You could also write it as t hat. That operator is equal to minus h bar squared over 2m times the second derivative with respect to position of what? Well, of the wave function. And finally, we have h hat, the Hamiltonian, which is an expression of the total energy in the wave function. It's a combination of the kinetic energy operator here, which you can see, first of all, as p squared. We have a second derivative with respect to position, and minus h bar squared. This is just p squared divided by 2m. P squared over 2m is a classical kinetic energy. The analogy is reasonably clear there. You add a potential energy term in here, and you get the Hamiltonian. Now, expectation values of operators like this are calculated as integrals. The expectation value of Q, for instance, is the integral of psi star times Q acting on psi over all space. This bears a striking resemblance to our expression, for instance, for the expectation of the position, which was the integral of just x times rho of x, where rho of x is now given by the absolute magnitude of psi squared, which is given by psi star times psi. Now, Basically, the pattern here is you take your operator and you sandwich it between psi star and psi. And you can think about this position as being sandwiched between psi star and psi as well, because we're just multiplying by it. It doesn't really matter where I put it in the expression. The sandwich between psi star and psi of the operator is more significant when you have operators with derivatives in them. But I'm getting a little long-winded about this. Perhaps suffice it to say that operators in the wave function allow us to calculate meaningful physical quantities, like x, the expectation of position. This is more or less where we would expect to find the particle. Or the expectation of p, and I should be putting hats on these since technically they're operators. The expectation of p is more or less the expected value of the momentum, the sorts of momenta that the system can have. Or the expectation value of h, the typical energy the system has. And all of these are tied together in the context of uncertainty. For instance, if I wanted to calculate the uncertainty in the momentum, I can do that with the same sort of machinery we used when we were talking about probability, that I calculate the expectation of p squared and I subtract the expectation of p squared. So the expectation of the square minus the square of the expectations is directly related to the uncertainty. So that's a little bit about operators and a little bit about the wave function and a little bit about how they're used. Operators acting on the wave function calculating expectations in the context of the wave function being treated as a probability distribution. Now, where are we all going with this? We're going towards the Schrodinger equation. And the Schrodinger equation, to write it out, is I h bar partial derivative with respect to time of the wave function, and that's equal to minus h bar squared over 2m second partial derivative with respect to position of the wave function, plus some potential function of x, times the wave function. Now the wave function psi here, I've left it off as a function of position and time. So this is really the granddaddy of them all. This is the equation that we will be working with throughout Chapter 2. We will be writing this equation for various scenarios and solving it, and describing the properties of the solutions. So hopefully now you have a reasonable understanding of the wave function and enough understanding of operators to understand what to do with the wave function. The sorts of questions you can ask of the wave function are things like, what sorts of energy does this system have? How big is the spread in momenta? Where am I likely to find the particle if I went looking for it? But all of that relies on having the wave function, and you get the wave function by solving the Schrodinger equation. So that's where we're going with this. And that's all of the material for Chapter 1. And without further ado, moving on to the next lecture, we'll start solving the Schrodinger equation. We're going to move now into actually solving the Schrodinger equation. This is really the main meat of quantum mechanics. And in order to start tackling the Schrodinger equation, we need to know a little bit about how equations like the Schrodinger equation are solved in general. One of those solution techniques is separation of variables, and that's the solution technique that we're going to be applying repeatedly to the Schrodinger equation. First of all, though, let's talk a little bit about ordinary and partial differential equations. The Schrodinger equation is a partial differential equation, which means it's a good deal more difficult than an ordinary differential equation. But what does that actually mean? First of all, let's talk about ordinary differential equations. What an ordinary differential equation tells you is how specific coordinates change with time. At least that's most applications. So you have something like x as a function of time, y as a function of time, sorry, not y as a function of x, y as a function of time, z as a function of time. For example, the position of a projectile moving through the air could be determined by three functions, x, y, and z. If you're only working in 2 dimensions, for instance, let me drop the z, but we might have a velocity as well, say vx of t and vy of t. These four coordinates, position in 2 dimensions and velocity in 2 dimensions, fully specifies the state of a projectile moving in 2 dimensions. What an ordinary differential equation might look like to govern the motion of this projectile would be something like the following. dx dt is vx, dy dt is vy. Nothing terribly shocking there, the position coordinates change at a rate of change given by the velocity, while the velocities change, dvx dt, is given by, let's say, minus kvx, and dvy dt is minus kv subscript y now, kvy minus g. This tells you that, well, where I got these equations, this is effectively damped frictional motion in the plane xy, where gravity is pulling you down. So in the absence of any velocity, gravity leads to an acceleration in the negative y direction, and the rest of this system evolves accordingly. What that tells you, though, in the end, is the trajectory of the particle. If you launch it as a function of time, tick, 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 as the projectile moves through the air in, say, x, y space. Partial differential equations, on the other hand, PDEs, you have several independent variables. So where in an ordinary differential equation we only had time, and everything was a function of time, in a partial differential equation, what you're trying to solve for will have several independent variables. For example, the electric field, the vector electric field in particular, as a function of x, y, and z. The electric field has a value, both a magnitude and a direction, at every point in space, so x, y, and z potentially vary over the entire universe. Now you know how, excuse me, you know a few equations that pertain to the electric field that maybe you could use to solve to determine what the electric field is. One of these is Gauss's law, which we usually give an integral form. The integral of the electric field dotted with an area vector over a closed surface is equal to the charge enclosed by that surface over epsilon naught. Now hopefully you also know there is a differential form for Gauss's law, and it usually is written like this. This upside down delta is read as del, so you could say this is del dot E, and this is a vector differential operator. I'm going to skip the details of this because this is all electromagnetism, and if you go on to take advanced electromagnetism courses, you will learn about this in excruciating detail. Perhaps suffice to say here that most of the time when we're trying to solve equations like this, we don't work with the electric field, we work with the potential, let's call that V, and this system of equations here, if you treat the electric field as minus the gradient of the potential, gives you this equation gives you the Laplace equation. Del squared V equals rho over epsilon naught. What that actually writes out to, if you go through all of the vector algebra, is the second derivative of V with respect to x plus the second derivative of V with respect to y plus the second derivative of V with respect to z, and I've left off all my squareds in the denominator here, is equal to rho over epsilon naught. This is a partial differential equation, and if we had some machinery for solving partial differential equations, we would be able to determine the potential at every point in space. And that would then allow us to determine the electric field at every point in space. This is just an example. Hopefully you're familiar with some of the terms I'm using here. The main solution technique that is used for partial differential equations is separation of variables. And separation of variables is fundamentally a guess. Suppose we want to find some function. In the case of electromagnetism, it's the potential, x, y, and z. The potential is a function of x, y, and z. Let's make a guess that v of x, y, and z can be written as x of x times y of y times z of z. So instead of having one function of three variables, we have the product of three functions of one variable each. Does this guess work? Well, it's astonishing how often this guess actually does work. This is a very restrictive sort of thing, but under many realistic circumstances, this actually tells you a lot about the solution. For example, the wave equation. The wave equation is what you get mathematically if you think about, say, having a string stretched between two solid objects. Now, under those circumstances, if you zoom in on, if you say, pluck the string, you know it's going to vibrate up and down. Mathematically speaking, if you zoom in on a portion of that string, say it looks like this, you know the center of this string is going to be accelerating downwards. And the reason it's going to accelerate downwards is because there is tension in the string, and the tension force pulls that direction on that side and that direction on that side. So it's being pulled to the right and pulled to the left, and the net force then ends up being in the downward direction. If the string curved the other direction, you would have effectively a net force pulling up and to the right, and a net force pulling up into, or a force pulling up into the right, a force pulling up into the left, and your net force would be up. This tells you about forces in terms of curvatures, and that thought leads directly to the wave equation. The acceleration, as a result of the force, is related to the curvature of the string. And how we express that mathematically is with derivatives. The acceleration is the second derivative of the position. So if we have the position of this string is u as a function of position and time, then the acceleration of the string at a given point and at a given time is going to be equal to some constant, traditionally written c squared, times the curvature, which is the second derivative of u with respect to x. Again, u being a function of position and time. So this is the wave equation. I should probably put a box around this because the wave equation shows up a lot in physics. This is an important one to know. But let's proceed with separation of variables. U, as a function of position and time, is going to be x, a function of, not time, x, a function of position, and t, a function of time. So capital X and capital T are functions of a single variable each, and their product is what we're guessing will reproduce the behavior of u. So if I substitute this u into this equation, what I end up with is the second derivative of x, t of t, with respect to time, equals c squared times the second derivative of x, t of t, with respect to position. So this hasn't really gotten us anywhere yet, but what you notice here is we have derivatives with respect to time, and then we have this function of position. Since these are partial derivatives, they're derivatives taken with everything else other than the variable that you're concerned with held constant, which means this part here, which is only a function of position, can be treated as a constant and taken outside of the derivative. The same sort of thing happens here. We have second derivatives, partial second derivatives with respect to position, and here we have only a function of time, effectively a constant for this partial derivative, which means we can pull things out. And what we've got then is capital X. I'm going to drop the parentheses x because you know capital X is a function of lowercase x. So you've got big X, second partial derivative with respect to time of big T, equals c squared, big T, second partial derivative of big X with respect to x. That's nice because you can see we're starting to actually be able to pull x and t out here. The next step is to divide both sides of this equation by xt, by basically dividing through by u. In order for this to work, we need to know that our solution is non-trivial, meaning if x and t are everywhere 0, dividing through by this will do bad things to this equation. But what you're left with after you divide by this is 1 over t, second partial of t, big T with respect to little t, and c squared 1 over big X, second partial of big X with respect to little x. This is fully separated. What that means is that the left-hand side here is a function only of t. And the right-hand side is a function only of x. That's very interesting. Suppose I write this function of t as, say, f of t. This part, let's call that g of x. I have two different functions of t and x. Normally you would say, oh, I have f of t and I have g of x, and I know what those forms are. I could, in principle, solve for t as a function of x. But that isn't what you're going to do, and the reason that's not the case is that this is a partial differential equation. Both x and t are independent variables. All of this analysis, in order for separation of variables to work, must hold at every point in space, at every x and at every time. So suppose this relationship held for a certain value of t and for a certain value of x. I ought to be able to change x and have the relationship still hold. So if I change x without changing t, the left-hand side of the equation isn't changing. If changing x led to a change in g of x, then my relationship wouldn't hold anymore. So effectively what this means is that g of x is a constant. In order for this relationship to hold, both f of t and g of x have to be constant. Essentially, what this is saying in the context of the partial differential equation is that if we look at the x part here, when I change the position, any change in the second derivative of the position function is mimicked by this 1 over x, such that the overall function ends up being a constant. That's nice, because that means I actually have two separate equations. F of t is a constant and g of x is a constant. What these equations actually look like. This was my f of x, and this is my f of t, and this is my g of x. That constant, which I've called a here, and the notation is arbitrary, though you can in principle save yourself some time by thinking ahead and figuring out what might be a reasonable value for a. What's especially nice about these is that this equation is now only an ordinary differential equation. Since big T is only a function of little t, we just have a function of a single variable. We only have a single variable here. We don't need to worry about what variables are being held constant and what variables aren't being held constant. So we can write this as total derivative with d instead of partial derivative with the partial derivative symbol. So we've reduced our partial differential equation into two ordinary differential equations. This is wonderful. And we can rearrange these things to make them a little more recognizable. You got d squared t dt squared equals a t, and c squared d squared big X d little x squared equals a times big X, multiplying through by big T in this equation and big X in this equation. And these are equations that you should know how to solve. If not, you can go back to your ordinary differential equations books, and solution to ordinary differential equations like this are very commonly studied. In this case, we're taking the second derivative of something and we're getting the something back with a constant out front. Anytime you take the derivative of something and get itself or itself times a constant, you should think exponentials. And in this case, the solution is t equals e to the square root of a times time. If you take the second derivative of this, you'll get two square roots of a factors that come down, e times e to the root at, which is just big T. You can, in principle, also have a normalization constant out front, and you end up with the same sort of thing for x. Big X is going to be e to the square root of a over c x, with, again, in principle, a normalization constant out front. What that means is, if I move things up a little bit, get myself some space, u of x and t, what we originally wanted to find, is now going to be the product of these two functions. So I have a normalization constant in front, and I have e times root a t, and e times root a over c x. Now, if this doesn't look like a wave, and that surprises you because I told you this was the wave equation, it's because we have, in principle, some freedom for what we want to choose for our normalization constant and for what we want to choose for our separation constant, this constant A. And the value of that constant will, in principle, be determined by the boundary conditions. A and A are determined by boundary conditions. The consideration of boundary conditions and initial conditions in partial differential equations is subtle, and I don't have a lot of time to fully explain it here. But if what you're concerned with is why this doesn't look like a wave equation, what actually happens when you plug in to your initial conditions and your boundary conditions to find your normalization constants and your actual value for the separation constant, you'll find that A is complex. And when you substitute in the complex value for A into these expressions, you'll end up with e to the I omega t sort of behavior, which is going to give you effectively cosine of omega t, up to some phase shifts as determined by your normalization constant and your initial conditions. So this is how we actually solve a partial differential equation. The wave equation in particular separates easily into these two ordinary differential equations, which have solutions that you can go and look up pretty much anywhere you want. Finding the actual value of the constants that match this general solution to the specific circumstances you're concerned with can be a little tricky, but in the case of the wave equation, if what you want is, say, a traveling wave solution, you can find it. There are appropriate constants that produce traveling waves in this expression. So to check your understanding, what I'd like you to do is go through that exercise again, performing separation of variables to convert this equation into, again, two ordinary differential equations. This equation is called the heat equation, and it's related to the diffusion of heat throughout a material. If you have, say, a hot spot and you want to know how that hot spot will spread out with time. Since this is a quantum mechanics course, let's move on to the time-dependent Schrödinger equation. This is the full Schrödinger equation in all of its glory, except I've just written it in terms of the Hamiltonian operator now. H hat is the Hamiltonian. The Hamiltonian is related to the total energy. I evidently can't spell total energy of the system, meaning it's, kinetic energy plus potential. And we have a kinetic energy operator, and we have, well, we will soon have a potential energy operator. What H hat actually looks like is it's the kinetic energy operator, which, if you recall correctly, is minus h bar squared over 2m times the second derivative with respect to position. And the potential energy operator is just it looks a lot like the position operator. It's just multiplying by some potential function, which here I'll consider to be a function of x. Now this is an operator, which means it acts on something, so I need to substitute in a wave function here. And when you do that in the context of the Schrödinger equation, you end up with the form that we've seen before. I h bar d psi dt equals minus h bar squared over 2m d squared psi dx squared plus v of x psi. So that's our Schrödinger equation. How can we apply separation of variables to this? Well, we make the same sort of guess as we made before. Namely, psi is going to be xt, where big X is a function of position and big T is a function of time. If I substitute psi equals xt into this equation, you get pretty much what you would expect. I h bar. Now, when I substitute xt in here, big X, big T, big X is a function only of position, so I don't need to worry about the time derivative acting on big X. So I can pull big X out, and what I'm left with then is a time derivative of big T.
This is then going to be equal to minus h bar squared over 2m times the same thing. When I substitute xt in here, the second derivative with respect to position is not going to act on the time part. So I can pull the time part out. T, second derivative of big